Okay, right, we'll get going. Good afternoon, everyone. Thank you for joining us for part 5 of the current statistics webinar series. I'm impressed that we've got this far. And you could say we've saved the best till last. So today we're joined by National Highways, who are going to talk to us about some of their methods with analysing collision data with statistical approaches. And I've been aware of some of these methods for a couple of years now, so really pleased that you guys have come along to talk us through some of them. I've just put a link in the chat for anyone who wants to catch up on any of the previous webinars in this series, or as part of the Road Safety GB Analyst Network series more generally. You can find those in the link on the chat there. So yeah, National Highways today, they're going to present to us, and then we'll have a bit of time at the end for Q&A. So as usual, please do use the chat throughout to talk about anything you want to related to the presentation, make any comments, and use the Q&A as well to fire in your questions, and I'll direct those to the team at the end. Great, right, let's get going. So I'll hand over to Liz. I think you're going to kick us off.
Yes, thanks, Nathan. Hi, everybody. So yeah, I'm Liz Buckingham-Jeffrey, also here with Jake Clarkson and Dan Pencross, and we're all statisticians in National Highways. So thanks for coming along today. So we're going to talk about, as Nathan said, some of our statistical methods that we use to compare collision and casualty rates between different roads. So hopefully the slides are working. So just to start off with some context, so who are National Highways? So we manage the strategic road network in England. So that's the motorways and major A roads, which is over 4,000 miles of roads. Dan, Jake and I work in the analysis division, specifically in the network analysis and statistics team. So we support the business with analysis into like a whole range of different things like delay, customer satisfaction, but I guess importantly for this webinar also road safety. So talk about road safety. So National Highways, we monitor road safety through lots of different methods. Safety is our organisation's first imperative, and there's lots of focus within National Highways on safety, but our main key performance indicator is the number of people killed or seriously injured on the strategic road network, and you can see the trends of that metric in this graph. However, because traffic volumes change year to year, it's kind of tricky to directly compare the numbers this year with the number last year, particularly as highlighted to all of us during the COVID period, and this lower number here. So we also monitor the killed and seriously injured rate per vehicle mile, so this number per vehicle mile, which looks a bit like this. So rates, as I said, help us compare over time, or kind of when we've got different roads with different traffic volumes. So it helps us with kind of fluctuating traffic volumes, but also like dramatic changes in traffic volumes like we saw in 2020. So hopefully in this webinar today, we'll kind of talk to you about how we kind of robustly compare to collision or to casualty rates. So in this example here, we've got the rate 2.2, 2.0, 7 and 2. So should we consider those as like roughly the same rates? So they kind of clear reductions. So statistics helps, these statistical methods kind of help us with those kind of questions, and kind of like help us interpret whether these numbers robustly show that the SRN is getting safer or staying about the same. So we're going to try and explain those methods today. So soon I'll hand over to Jake, and in the first part he'll kind of explain what is maybe a commonly used method for analysing collisions. So using Poisson process, we'll try and explain that in a way that everyone can understand. And then the next part with Dan is like an extension to that method that we came up with. And then in the third part, I'll talk about applying those methods. So I'll hand over to Jake.
Thanks, Liz. Hello everyone. Yeah, just picking up on where Liz left then. So yeah, Liz was talking about comparing collision rates from year to year and statistical methods to do that. So, but first you might be wondering, well, why do we need statistical methods to compare collision rates? Why can't we just look at which rate is higher? And so to demonstrate why it's a bit limited doing that, I'm going to run through an example where we want to compare to safety on two roads. So let's say that since just after COVID, mid 2021, we've got two roads, Road 1 and Road 2, and we've observed 100 million vehicle miles on each. And let's say that on Road 1, we've seen 6 collisions, and on Road 8, we've seen 8 collisions. So a real simple conclusion that we could make is we could say, well, 6 is less than 8, so that means that Road 1 is safer. But so why is it though that this conclusion is a bit limited? Now, it isn't, or at least we're going to assume it isn't, an issue with the data. We know that Stats19 isn't perfect, but it is a pretty reliable data source. It's validated, so there shouldn't be any errors in the data, and it covers the whole of Great Britain. So it's not as if we're just observing a sample of collisions from a wider population, which is a common hurdle in statistics. We are observing the whole population of collisions on these roads. So what is it that makes the conclusion limited then? Well, it's that this simple conclusion ignores that underlying safety isn't the only thing that's influenced those collision counts of 6 and 8. Random chance, luck, variation, whatever you want to call it, has also played its part. And I'm going to demonstrate this a little bit more with a football example. So I want to look over similar timescales since mid 2021 at which of these two teams, Manchester City or Tottenham, has played the better football. And just a quick disclaimer, you can't accuse me of being biased because I don't support either of these teams. So the most obvious thing I'd say to look at is probably the results when both these teams played each other over that time period. So here in this in this kind of graphic here, we've got the dates down the left-hand side of matches between the two teams, the competition, and then how many goals each of the two teams scored, with the winning team, if there is any, unless it was a draw, being in bold. So the most obvious thing to do to determine which team is better is just to count up which team has won the most of the head-to-head matches. And if we do that, we see that Tottenham won 6 and City won 4. So that means the simple conclusion would be that Tottenham have been the better team. But first, just to demonstrate one element of this random chance and luck, I did a little bit more digging into these matches and found that in 3 of the older matches, City hit the crossbar, the frame of the goal, with a shot, whereas Tottenham did not. And if you look at the results in those matches, if that shot that hit the crossbar had gone in, it would have overturned the result, either from a Tottenham win to a draw, or in one example, from a draw to a Manchester City win. So what that means is that with the goal frame just being slightly larger, the record would have read Tottenham 4 wins, City 5 wins, and we would have made a completely different conclusion. That just shows how these simple conclusions can be quite fragile in certain cases. And there are similarities between the football example I've just mentioned and road safety that we're looking at, in that they measure either ability or safety via goals or collisions. And goals and collisions are both quite rare events, so they're not something that's happening all the time. And we can also have near misses. So, for example, in the football example, the crossbar, as I've mentioned, or maybe a marginal offside where a team gets close to scoring but doesn't. And we can have the same thing in the safety example, maybe with close shaves where two vehicles nearly hit each other, but one manages to swerve out the way. And that could have been the case there could have been a lot more of these close shaves on Road 1, for example. Now, what these near misses mean is that safety or footballing ability is not always either rewarded or punished in the data, because a near miss doesn't show up in the data. And something else to note is that the data is also influenced by, or can be influenced by, external factors which aren't actually reflective of either safety or footballing ability. So, as an example, in the football case, I've noted that Tottenham played Manchester City twice in a month, which was just after City had lost a key player to injury, so we're adapting to that. So that was quite a fortunate time for Tottenham to play City. And a similar example in road safety could be that Road 2 just happened to have more reckless motorists driving down it, something that isn't indicative of safety, but it's just kind of almost bad luck on Road 2's part. So these, let's say, number of near misses and favourable, unfavourable external factors, they will even out over time, but over a finite time period, you can see how one team or road can just appear to be better or safer than the other, just due to random chance. And the fact that collisions and goals are quite rare events mean that it will take a longer period of time for these luck chance-based factors to even themselves out. The sort of statistically, what we would say is that there is some underlying true collision or ability rate, which we'll call lambda, that we can never measure exactly only with a finite amount of data. And that what we can do with a finite amount of data is get a noisy estimate of this lambda. So, for example, that would be the 6 collisions that we saw on Road 1. That would be a noisy estimate of the true underlying safety rate. And it's that noise that we have in our estimates, that's what leads to the uncertainty and why there is uncertainty to quantify. Okay, so we've justified that we can't just naively compare collision rates or number of wins over a finite period because there is this uncertainty which comes about due to external factors or random chance. So now I'm going to talk about what affects the level of this uncertainty. So I've put up those 2 naive conclusions from the past slide. Now, for those people who know a little bit about football, why is it that you look at that football-based conclusion and you know that it's clearly problematic? And the reason for that is that Manchester City won the league 3 times from 2021 to 2024, then came 3rd last year, whereas Tottenham did okay, but weren't really close to winning the league in the first 3 seasons, and then had an absolute stinker last year. So, in other words, we've got, in the football example, we've got more data. We've got the results against other teams. So that chance or luck of maybe be injuries, crossbar hits, refereeing decisions, etc., it's got a lot of time to even itself out. They say that the best team always wins the Premier League. That's because it's played over 38 matches, almost 3,500 minutes. Now, the same effect does occur for road safety. As we observe more and more traffic, more and more vehicle miles, there's more time for this chance, so say the number of close shaves or proportion of bad drivers, to even itself out over different roads. And we can observe more vehicle miles either by expanding the time window that we observe a road for, or maybe the length of road that we're looking at. So i.e. we can expand both temporally or spatially. I've just put some rough examples in a table here to show you what I mean. So let's say in the first row, we're just looking at a single road, the M55, which is a smaller motorway connecting Blackpool and Preston. And we're just looking at it for a week. Suppose we see about 2 million vehicle miles. Then there's quite high uncertainty in any inference I would make about the true collision rate, which remember we called lambda in the last slide. And the reason for that is that collisions are quite rare. So I've not really got enough vehicle miles for these external factors and random chance to even out. In other words, it's not guaranteed that the collision rate I calculate from the 2 million vehicle miles of data is a good reflection of the true collision rate. And now let's say in the second row that I expand temporally to a whole year. I've got more vehicle miles, 100 million now, so my uncertainty drops to medium. And then if I expand spatially to say all the motorways in Lancashire in the third row, the uncertainty drops further. And I'm more confident that the collision rate, which is the noisy collision rate, which I calculate from 10 billion 10 billion vehicle miles, is close to that true underlying rate. Now, here in this table, in the final column, I've just written some high, medium, lows off the top of my head. What we really need is a way to quantify or formalize this uncertainty. And that is where the Poisson process comes in. Now, you may have heard of a Poisson process before, but I'm going to introduce it here whilst kind of demonstrating that it's not a highly specific modelling choice we make with a sort of a ton of assumptions. It comes about very naturally, and that all we in fact need to assume is that for a given road, the collision rate, which become true collision rate, which we call lambda, is the same at any point in time, no matter what's happened with recent collisions, and that a Poisson process will fall out of this one assumption. So implications of this assumption, well, firstly, it means that collisions must be independent, since the occurrence of one collision cannot affect the collision rate because the collision rate is the same at any point in time. It also means that whenever the last collision occurred, the expected or average amount of vehicle miles from right now until the next collision must be the same. So essentially, it means there's no concept of, oh, we haven't had a collision for a while, or we must be due one, because the collision rate is the same at any point in time, no matter what has happened. And we call this second bullet point the memoryless property. In particular, it's the time between consecutive collisions that is memoryless. And there's only one distribution in continuous time which has this memoryless property, and that's the exponential distribution. So it's only the exponential distribution that we can use to model times between collisions. So I'll show you what this looks like now. So on the x-axis, I've got vehicle miles and going up continuously in time. And on the y-axis, I'm counting collisions. I'm going to mark collisions with a blue circle as in the bottom left. Now let's suppose that the first collision happens after some number of vehicle miles. Then, if we recall where lambda is the collision rate per vehicle mile, to fit with our sole assumption and have this memoryless property, the gap between collision 1 and collision 2 has to follow an exponential distribution with rate lambda. And we have the same thing between collision 2 and 3, and then 3 and 4. And to sort of demonstrate the second bullet point about the memoryless, let's look at the expected or average vehicle miles we will see until collision 5 happens. And this expected amount is the same at any of these three red crosses, be that just after collision 4 has happened or a while after collision 4 has happened. And from a property of the exponential distribution, this expected amount of vehicle miles until I see next collision is 1 over lambda. So to summarize, the expected vehicle miles until the next collision is going to be equal to 1 over lambda at any point. And because it's 1 over lambda, the greater the collision rate lambda, the smaller the expected vehicle miles until the next collision. Okay, so you'll be thinking, well, I've been banging on about exponential distributions. Where does the Poisson come in? Well, the exponential distribution and the Poisson distribution are linked, so that the total number of collisions that I see in some v vehicle miles follows a Poisson distribution, and the rate of that Poisson distribution is the vehicle miles v multiplied by the collision rate lambda. And this is what we call a Poisson process with rate lambda. Okay, so just to summarize, if we wanted to model road 1 as a Poisson process, we would assume that there's some underlying rates, say lambda 1, which is the true collision rate per 100 million vehicle miles. And also what that means is the number of collisions in these 100 million vehicle miles will follow a Poisson distribution with rate lambda 1. And note that using rate per 100 million vehicle miles is an arbitrary choice, but we prefer to do that rather than lambda being the rate per vehicle mile, because otherwise lambda would be very small. So remember as well that lambda 1 cannot be observed, but what we can do is we can learn about it through data. So let's go back to the example that I showed you before. And remember, for road 1, we saw 6 collisions in 100 million vehicle miles. And what that means is under the Poisson process model, this 6 is one observation from a Poisson distribution with rate lambda 1. So what does this observation tell us about lambda 1's true value? Well, remember that lambda 1 represents the true collision rate per 100 million vehicle miles. So observing 6 collisions in 100 million vehicle miles is kind of evidence that lambda 1 is around 6. But because 100 million vehicle miles isn't actually that many, we've only seen 6 collisions in this time, there's a lot of uncertainty in this value. And we can see this uncertainty in this distribution plot of lambda1 based on 100 million vehicle miles, which theoretically comes out of the Poisson process. Remember, we never actually see lambda1. Now, the higher the curve, the more likely that the value on the x-axis is the true value of lambda1. And we can see that it's centered on 6, but there is a decent chance that it could be as high as 8 or as low as 4. We've got the probability there on the y-axis. And we can do the same thing for lambda2. So we saw 8 collisions. That's one observation of a Poisson lambda2. And we see that lambda2 is centered around 8, but again, there's significant uncertainty. So a conclusion that we could make from seeing 100 million vehicle miles of data about which road is safer, so in other words, which of the lambdas is larger, we'd say, well, it's most likely that lambda1 is less than lambda2, but because there's sort of significant overlap in these distributions, it could be the other way around. It's far from guaranteed that road 1 is safer. Now suppose that instead we observe 5 times as many vehicle miles, so either observing more of the road or for a longer time period. And suppose that the observed rate per 100 million vehicle miles is the same, so we've still got 6 and 8. So we observe 30 in 500 million vehicle miles for road 1 and then 40 for road 2. Now, as I said in the previous slide, the uncertainty drops because we've got more opportunity for random variation, external factors to even themselves out. And the Poisson process recognizes this. So the uncertainty, or the standard deviation, is now 5 times lower. So the distributions for lambda1 and lambda2 are a lot more pointy. And if we keep lambda1 and lambda2 as the rate per 100 million vehicle miles, we're now very confident that lambda1 is between 5 and 7, and that lambda2 is between 7 and 9. So lambda1 being smaller, than lambda2 is almost guaranteed. So we can say that road 1 is safer than road 2 with a lot more confidence, although not quite 100%. So now I'll hand over to Dan, who's going to talk about formalizing this testing process and also an extension to casualties.
Cheers. Thanks, Jake. So as Jake said, I'm now going to run through the the practical application of this sort of theoretical background. So we'll start off with same observation that Jake made about those 2 roads. We've got road 1 with 6 collisions per 100 million vehicle miles, road 2 with 8 per 100 million vehicle miles. So from that, we formulate a question. The question is one road safer than the other? Because we can't really tell that, as was highlighted, just by looking at those values. And so with that question, we formulate our hypothesis, and that is the mean of the collision distributions, which we've just been shown, are significantly different. Now, you will notice here that I've changed this notation that Jake was using. So he was using lambda. We're using lambda hat, and the hat here implies that it's an observed value rather than the sort of underlying value. So these are values that we actually observe from the data. Speaking of that data, we need to, so what we're going to do with that data is we want to ultimately test these hypotheses using significance tests. And in order to formulate those significance tests, we need measures of uncertainty in that data to calculate our confidence intervals. So in order to do this, we need to generate potentially some data, because we can't actually wait for the natural data generation process to give us enough data to reduce this uncertainty. We need to report every year. So instead of waiting for the natural data generation process, we want to construct a bootstrap distribution. So we use the Poisson distribution to do this, using the observed collision rate and the number of vehicle miles driven on each road, we generate almost like parallel universes of our year's worth of data. So this N on the screen here represents the total number of collisions over the course of a year, and then we will generate using the Poisson distribution a set of values of n, which will ultimately give rise to a distribution very similar to the ones that we were just shown. And the more we do this, the more we can reduce the uncertainty value. So as we build up our distribution, ultimately, we can see that we get our lambda 1 distribution and our confidence interval. Now here, this is just a representative of a 95% confidence interval because that's what is sort of convention. So we've got this for road 1 and we've got it for road 2. So we're representing many parallel years of worth of collision data here. Once we've got this, we can then compute our confidence intervals for both lambda 1 and lambda 2, and then that gives us our measure of uncertainty. So the means of our collision distributions are this 6 and 8 as we fed in originally. With that and the confidence intervals, we can then perform our significance tests. Now there are a wide variety of significance tests that you can use. Sort of the standard ones are a z-test and a chi-squared test with 1 degree of freedom. They're quite commonly used. There are also others, and in our sort of investigations that were originally done, they identified that it's also possible to use a c-test and an e-test, which are less common. Ultimately, we arrived at the decision to use a maximum likelihood ratio test, which is a Monte Carlo process, which fits in with this data generation. Whichever test you use, ultimately, you then have to interpret a p-value, and then you decide whether or not you're going to accept or reject your null hypothesis. That we're not going to go into the details of. There are lots of different descriptions of this, and I imagine people are very well versed in accepting and rejecting hypotheses. Both ROSPA and DFT have documentation about the use of these tests. There is, however, a statistical hazard. We've been throughout this talking about collisions, but there is another step in the process where we want to learn about the uncertainty in casualties as well, and that poses a problem because, as has been highlighted previously, the problem with casualties and where the statistical hazard comes about is that for each collision that's recorded can result in more than one casualty. And how this has an effect on the Poisson process as a whole, I'm going to explain now. So if we go back to the football analogy that we saw earlier and to extend it to cover this scenario, if you imagine a slightly different world where football isn't played quite as deterministically as it is now, you score a goal and then there's a slight modification where the referee rolls a dice and then the points that you score are equal to the die roll. So how does that fit with our model? So the number of points a team scores does not depend only on the number of goals they score. So how does this fit with our model of collisions and casualties? Well, you can imagine that instead of a goal, you've got a collision that occurs. Then once that collision has occurred, here in the similar way to Jake did, the blue, in this case ovals, are going to represent collisions. So once you've got a collision has occurred, you've then got a risk of injury. So it's not a deterministic process. Just because a collision has happened does not mean necessarily that there are going to be casualties. However, there may well be. So your casualties result from your collision. So in this case, we've got one collision that's got 3 casualties. So whilst the collisions are still, the vehicle miles between them are still exponentially distributed according to the collision rate, the vehicle miles between each casualty happening are not, they do not follow that same distribution. Some of them are happening instantaneously, groups of them are occurring with the collisions, but they don't follow that same distribution, and you can get different numbers of them occurring with each collision. So just the collisions are still distributed in the same way. The casualty rate is not as easy to parameterize as the collision rate. And so this violates the independence condition that Jake identified earlier of the Poisson process. So you can't say that casualties are the direct result of a Poisson process. So what can we do? We want to be able to determine the uncertainty in our casualty rates. We want to make these significance tests. We want to formulate hypotheses and be able to accept or reject them. So we need to extend the process. And how we do that to model casualty rates is we use what's called a compound Poisson process. So we've got our model, collision occurs, there's a risk of injury, and then casualties result from that. So your casualty rates can be modeled by this compound Poisson process, which is you get your generating event, which is Poisson distributed, and we've already identified collisions themselves are Poisson distributed. And then the follow-on event from that can follow any distribution. It's just, it has to follow on. There has to be a distribution following that initial event. So whilst we were doing this work, many different parameterizations were investigated for this specifically, this process going between the risk of injury and then casualties. There were Poisson, negative binomial, geometric. All of those had poor fits to the data, and it's hypothesized that that was further complicated by the fact that the distribution of casualties is truncated, because in Stats 19 there's always at least one casualty associated with each of those events. So there are no events with 0 casualties. So there's a truncated distribution there. So ultimately, we've formulated the hypothesis that it's a mixture of distributions that give rise to casualties, and pragmatically, we decided to adopt a non-parametric approach. So we said we'll leave that for another time, those distributions, and we're just going to do this non-parametrically. So compound Poisson process is 2 steps. So just as I identified previously, we start off with step 1, where we have our observed collision rate, lambda hat, and then we generate a number of collisions for each year and do that multiple times to give us our distribution of annual collisions. Now that's our parametric bootstrap. We've parameterized this value n with the Poisson distribution. Then step 2, which is the sort of the novel step as part of this work, was then for each of those collisions in a year, we sampled the number of casualties per collision. So we looked at the distribution of casualties and said, right, so for each of these collisions, we will associate that with a random choice from the data set of how many casualties resulted from each of those collisions. And then with that, we have our distribution of casualty rates, which is now our non-parametric bootstrap. So we've done that as a solely data-driven process. And with that distribution, we can then do inference, just like we did before. We can compute confidence intervals, we can perform significance tests, and we can then accept or reject our hypotheses, which obviously we made before we started this process. Okay, and then with that, I'm going to pass back to Liz to go through the conclusions.
Thanks, Dan. So hopefully now you've all got some understanding of the statistical work that we did. So from kind of noticing that casualties are not independent, we investigated how then we could model casualties without like deviating from this kind of accepted and widely used like Poisson process method for collisions. That led us to this compound Poisson process, and then we've used that to kind of think about developing kind of confidence intervals on casualty rates. So when I kind of say the thinking like that, it all sounds simple, but kind of the work took us to kind of do this thinking, took us 2 years because we were, well, because it was tricky, and we were ensuring it was kind of thoroughly reviewed and assured. So I just wanted to kind of talk you through some of that process. So we developed and thought about these methods within our team. We asked the ONS, Office for National Statistics, to do a kind of review. We tried to seek input from as kind of many others as we could while we were thinking about this stuff. We got also a kind of external review and statistical input and kind of like subject matter expertise in stats from John Torn at Lancaster University. And then we wrote about everything that we thought about, and we put it on, published it on the National Highways website. And we said, this is kind of what we're thinking, and we asked widely for feedback. And that all took us 2 years. And then the next thing we did is then we kind of used these methods, and we used them in these second, third and fourth year progress reports on the smart motorway evidence stocktake. So this method development was driven by smart motorways. So national highways were recommended by the Office for Road and Rail, which are our regulator, to develop statistical methods to robustly compare collision and casualty rates between different motorway types. It was kind of like the driver for us to think about all of this so carefully. So compare kind of conventional motorways with all lane running motorways, controlled motorways, dynamic hard shoulder motorways and major A roads, to compare those collision and casualty rates really robustly. So the methods have been used in that application as well as others, and those reports were also checked and assured by people. So we've tried to do a lot of kind of try and get lots of input from other people on these methods, but kind of any input from anyone on the webinar today would be interested to hear as well. So I'm going to now talk you through some of these results from applying these methods to the smart motorway example. Oh, and just to highlight, yes, we thought about this stuff really carefully, but there's still some limitations. So adjusted KSI rates, so when KSI numbers have been adjusted because of the changes in the severity reporting in Stats 19, that poses a problem because then you don't have integers, and that's a bit tricky. So yeah, we've thought about it really carefully, but there's still limitations. So I guess just to kind of highlight why these methods help. So here are collision rates for kind of some different road types, just as an example. So those A roads, and then the different motorway types that we have. So we have conventional motorways, controlled, all lane running and dynamic hard shoulders. So these might be the different collision rates that we see, and then the questions that we get asked are like, these look quite similar, and these are kind of similar. So that's when we get asked as statisticians, like, can you kind of more robustly compare those? That's kind of what started all of this. And then, these methods help us be able to put these kind of confidence intervals. So here's some actual kind of results. So these are the results that were published in our fourth year progress report on the smart motorway stocktake and action plan. So published in December last year. So that's our last publication on this, our last annual publication. So what do we notice? So these are the collision rates here. So you can see that the confidence interval for the conventional motorway is narrower, and that's because there's higher traffic volumes on conventional motorways. We've got more conventional motorways, so there's more traffic. So kind of, as Jake was saying at the start, we kind of have less uncertainty because we see more happening on conventional motorways than the other types of motorways, which we have fewer of. And then the conventional motorway rate and the all lane running motorway rate are quite similar. We look at our confidence intervals, and they do overlap a little bit here, but doing the significance test, where we got a p-value of 0.01, and we concluded that they are different. The same for the controlled motorway rate and the collision rate and the dynamic hard shoulder collision rate. So again, those confidence intervals overlap, so by a bit more this time, but when we did a significance test we got a p-value of 0.031, so we kind of said, oh, that feels different. And then thinking about casualty rates, so these confidence intervals here, so they were derived from that compound Poisson process, that two-step process that Dan explained, where we kind of sample from a Poisson distribution and then from the casualty per collision distribution, smush those two together to get our uncertainty around a casualty rate. So I guess what we notice here, so all of these intervals are wider than the intervals for the collision rates because of that two-step process, so there's more uncertainty. So there's the chance that you're involved in a collision and then the chance that you get injured from being involved in that collision. So there's more uncertainty. So there's a bit kind of wider rates. I think this scale here goes to 14 and the scale on the plot before went to, sorry, this scale goes to 20. The scale on the plot before went to 14. So there's a lot of overlap between the casualty rates of the controlled motorways and the dynamic hard shoulder motorways. So we're kind of saying like there's no evidence that these underlying casualty rates for these road types are different. And there's still some overlap between the casualty rate of the conventional motorways and the all-lane running motorways. So there's kind of some evidence of a difference, but we're not kind of very confident. So we're being kind of cautious in the conclusions that we make there. So we're saying that there is kind of, we haven't got any evidence that those are different. So I think these are our, that's the end of what we've prepared. So these are our conclusions. So we've developed these robust processes to compare collision and casualty rates. And I think for us, kind of having those robust processes are really important, and having the right assurance and review of these methods was really important. So we really did go back to the beginning in our thinking, like, yes, we've been using these Poisson process based hypothesis tests for ages in national highways with collisions, but we really wanted to go back to the start and think about, okay, where does that come from? Is it okay to use it with casualties? And then work through all of those steps as Jake kind of explained. And we also really tried to work on getting the comms right. So how do we explain some of these things to non-statisticians? How do we write about these things correctly? And we've really tried in our reports to be careful about how we write about p-values and interpreting p-values and drawing conclusions from them. So we're trying hard on those things. Yeah, if you've got any questions for us, I think we've got a bit of time. But yeah, thank you for having a listen today.
Great, thanks very much, Liz, Jake, and Dan. Right, questions. I can't see any questions in the Q&A, so I've always got questions. So I'll start maybe with a question or two, and then we can fire away from there.
There's a hand up, Nathan. Yeah,
I can see a hand from Kate, although Kate is muted and can't share video. So if you've got a question, Kate, then please chuck it in the Q&A. I think that's probably easiest, unless somebody behind the scenes can unmute you and whatnot. And I think that's what we'll have to do. In the meantime, though, if I'm sat here as a local authority analyst, maybe, and I'm seeing that you've spent 2 years developing these methods. Let's not reinvent the wheel where we don't have to. They've been through lots of assurance. You've engaged academics, etc. You've applied them for smart motorways. And I'm a local authority analyst thinking, how could I engage with this? How could I be applying these? Maybe we've got a small sample size of roads, less robust data to deal with as well. Where could I start in terms of using what you guys have done at a local authority level? Because I note actually in the document you produce with this, you do comment on the fact that you've developed these methods and you hope that they could be developed further and used more widely. So yeah, where could I start with using these things?
Yeah, so on our website, I should have maybe put the link on the slide. On our website, we put out our document kind of explaining these methods and thinkings, and in the annex of that are all the kind of I guess algorithms, for want of a better word. So that kind of explain that we, to get the confidence interval, for example, we would first sample from a Poisson distribution with this rate, and then sample from the casualties per collision distribution, and then put those together. So it's not going to lie, it's a reasonably technical statistical document, but I think the algorithms at the end are reasonably kind of well described. So we coded those algorithms originally in kind of a few years ago in R. So we used that statistical software R because we went down the kind of more numerical bootstrap approach. The maximum likelihood ratio test is we have to do lots of sampling, so you can't really easily do that in something like Excel because you have to kind of sample repeatedly, and the more you can do that, the better. I think recently we've also been kind of converting those over to Python because that's what we're starting to use more and more and more in our team. And I guess so. Yeah, I guess my starting point would be to direct people kind of there, and then get in touch with us. I think when we put that out, we said his email address to get in touch with us. So I guess at the time we were kind of welcoming comments, but we, very much welcome people that wanted to chat with us about this.
Great. Question from Axel. Can always rely on you, Axel, for questions, which is great. How would you use this approach for KSI, or I guess FWI fatal weighted injury collisions and casualties, including adjusted KSI? So how could you build on what you've done for those specific kind of collisions? Any thoughts on that?
Yeah, so it's the methods work. These methods work fine for KSIs. So we've been looking at, and when we've described this, we've talked about like all collision numbers, collision rates or casualty rates. But it's kind of equally fine to apply them to KSI rates, so to subsets of collision rates or FWI. The issue comes with the adjusted KSIs. So adjusted KSIs, so that's the adjustments for the way, I don't know all the background, but the way that the severity is reported by the different police forces. Some are using a different system, and some have transferred over to the new system, and then that means that the ones on the old system are adjusted. So that is tricky, and we've not solved that bit because the reason that's tricky is because KSI rates, that's just a count of the people that were killed or seriously injured, so that's fine. That's like Jake was saying at the start, that could be like 6 casualties or something, but an adjusted KSI count it's not an integer, like it's like, because of the adjustments you end up with like something like, I don't know, 6.8, which is tricky, right? Like that's not a sample from a Poisson distribution. So that just felt too difficult for me to think about. And so far we haven't been able to apply these methods to KSIs, which is tricky because that's like our main metric. So we just kind of at the moment have to acknowledge that limitation, and we apply it to collisions, and we can apply it to like FWI collisions, or can we apply it to we apply it to kind of subsets. So when we're thinking about just certain types of collisions, like in the smart and motorway context, people are interested in collisions where one vehicle was stopped. So we've applied it to kind of like that subset of collisions, but we've just had to apply it to all casualties for now, and not KSIs. I guess we could apply it to just all fatalities if we wanted to as well. That would be doable.
Great. I can see Kate's put a question in the Q&A, but I wonder if I might not do it justice if I try and ask that. So Kate, I'm going to try and unmute you and allow camera, so you can ask this yourself.
Hiya, can you hear me?
Yes, can hear you. Great.
Excellent. Yeah, so we've been looking at a number of schemes. I'm thinking about the how do we balance the detailed numerical analysis, and I love what you've shown, really, really helpful, versus the detailed individual incident. You look at the detailed written description, and it says, driver fell asleep, rolled vehicle, crushed an overturned car, no other vehicles involved. The nature of that collision is very different from somebody who made a sort of judgment error. The nature of collisions in terms of their preventability varies. Is it a shortfall in the infrastructure? Because the implication of all of this is, what are we going to do as a result? It's the sort of the so what question. And if you had two identical routes with identical collision numbers, one might be of collisions which are eminently preventable, and you get a massive return on investment from changing them, and the other might be, as the route that we looked at, which Axel was involved in as well, which is a real head scratcher for us, where pretty much with only one exception, every fatal and serious injury and most of the slight injuries were completely unpreventable. Car breaks down, bursts into flames, passengers get out, run over by a following vehicle, motorcyclist evading police, filters between vehicles on a slip road, hits a vehicle, falls off, killed. HGV goes through VRS onto the dual carriageway below. HGV goes through VRS off the trunk road, compliant, fully standard VRS. It just loads and loads and loads of things like that, totally untargetable. So it's where do we go with it, I guess, is the question.
Yeah, no, really good question. So that's what I'm going to say. Probably not going to give a satisfying answer. So I get my thoughts as you were kind of speaking. I think what we've described here, these kind of like statistical methods, they kind of answer one question, one kind of specific question that we were getting, which is like, look at the national picture over a year, which we, the team that me and Jake and Dan is in National Highways is like our kind of national analytical teams. We have analytical teams that do look really, in detail of specific regions and roads. So, the questions that we were getting were like, on a yearly level for all of the strategic road network, can you compare these collision and casualty rates? And so I think, this kind of analysis, this kind of stats is really good, but also, collision investigation, looking into those, the causes of a specific collision, also really good. I think they go together. I think we need both of them. I think they're both helpful. I don't think, we can't just say, oh, here's a formulaic statistical test we can do that takes out any need to do what you were saying, which is like, look at the road, think about what's happening. So I think, we need both of it. I think this doesn't replace the other one. It's just more evidence. So what me, Dan, and Jake do quite a lot is we kind of help National Highways by, providing some evidence to kind of help make a decision or help think about something. But it's usually like one part of the picture. So like, here's, one puzzle piece, and what you were describing is another puzzle piece about that road, and there might be some other puzzle pieces as well. And I think we've got to put it all together. It's not just one bit of analysis or one method that is the best. It's all kind of complementary and all helps build an understanding to make a decision.
No, that's really useful. But it's not an easy, determining that return on investment, how do you get value for money, is tricky. We're trying to justify expenditure, and we know, traditionally casualty reduction schemes have delivered a really good return on investment, but they're ever diminishing as the things we can do. Vehicle technology will do a lot of the heavy lifting for us. Vehicle protection, both for people outside the vehicle and people inside. But what we do with the rest depends on knowing the details of the incident. And it's how do we blend those things? It's not an easy answer. I wonder whether you could use AI to scrutinise the written description circumstances free text field. It's hard enough to get that free text field, never mind do analysis of it, but I don't know if anyone's smart enough to do that.
Yeah, we are doing, that's probably maybe what Dan's put his hand up. Dan hears AI and he's like, we're doing some kind of free text analysis of not collision text, but other free text that we've got in a different project. Dan, did you want to jump in?
Just to say exactly that. There are Multiple different, so the field of natural language processing comes in clutch in that scenario. You can do in this case, you'd want to do something like topic modeling to pick out whether there are consistently the same things being noted, and I suppose you could also get round some of the I'm not an expert in the free text fields within Stats 19, but if those free text fields are filled out in a fairly arbitrary manner, like for each police officer who fills them out, they may fill them out slightly differently. So they could, so a system like that could identify where there are slight differences but group them together under the same heading, so you can pick out trends more reliably potentially there. But yeah, that is definitely an area that one of the actually sort of useful applications of the sort of artificial intelligence subdomains.
Thank you.
Yeah, go on, Jake.
Oh yeah. I was just going to say, Kate, what you were describing about different types of collisions. Some like car sets on fire could happen on the safest road ever. Other collisions could be as a result of the road not being designed in a safe way. It kind of almost seems like you could maybe try and do two separate analyses once you've done this kind of AI sort of sorting out, and almost looked at the rate of collisions which are just almost could happen anywhere, and ones that are more linked to the safety of the road potentially. But then the problem is, of course, that you end up with less data. It kind of almost made me think back to the football example. It's a bit like some goals could be like a beautiful passing move, it's a beautiful sort of football. The other ones could be you have a shot from 30 yards going towards the corner flag, takes a wicked deflection, and there's nothing the keeper could do about it. And the second one isn't very reflective of footballing ability. But then again, linking back to the football thing, you think that those kind of goals and the kind of collisions which aren't really anything to do with the road will even themselves out in time. But again, then you come back to the problem of collisions being so rare that it takes a lot of time for those kind of things to even themselves out, and that's maybe why on the finite amount of time you do need to it would help to look into the data a bit more, a bit like you and Dan were suggesting, to try and filter out which ones are very much reflective of the road not being safe, and which ones are just almost acts of God.
Thank you.
I feel like we could keep talking about this for a while. I can tell you're a football fan, Jake. I personally love the football analogies. I think they're quite helpful. Maybe not for everyone on the call. Great, thank you.
I had to get Jake to explain some of the football terminology.
Yeah,
before we
fair
started.
enough.
I was like, what? You're saying Spurs, and then you said Tottenham. Are they the same people? Yes, they are, but
you have to be very careful. Keep saying Tottenham. To confuse anyone.
Okay. No, that makes sense. But no, I found that really helpful actually, as a football fan myself. Cool. Thank you, Liz, Jake, and Dan for coming along. I found that really interesting. So that concludes our webinar series on best practice statistics. So we've heard from a number of different people, obviously National Highways Today, TRL, Transport for London, Devon County Council, and myself and my colleague Drishti at Agilitis as part of that series, a flavour of how we're all using stats and the kind of things we want to be using it for more. I don't want this to end there in terms of stats. So I know a few of you have emailed me already on various different bits, and those of you I haven't got back to, I will soon. If you want to talk about stats more, National Highways colleagues today have said they're very happy for you to get in contact with them. I'm also very happy to talk about this further and receive emails, etc., and have suggestions for future webinars in terms of what might be interesting in this space. So yeah, thank you for joining us today and for the rest of the series. One final thing, so joining the DOTS next year, I know a number of you have already booked your tickets, but just a reminder, that will be March next year, our kind of annual Road Safety GB Analyst Conference, to bring a lot of these topics and more together. The reason we haven't yet put out loads of stuff on the agenda is because we are eagerly awaiting the road safety strategy and want to build that into the agenda in terms of what that means for analysts in that discussion. So things will probably come out a little bit more after that. But yeah, just a reminder, if you haven't booked tickets and would like to come, then please do. All right, thanks for your time, and stay safe. See you soon. Have a good Christmas if I don't see you before.
Thanks,
Thanks, Nathan.
Nathan.
Thank you.
Bye.
Thank you. Thanks.